In this video, I want to take a look at a couple of examples of bases in different vector spaces. First of all, let me just say the singular is basis. And if you have several of these things, what do you call them? Are they bases? Or I think the accepted way is to call them bases, even though it looks like it's bases. Bases as opposed to basis, like parentheses and parenthesis. Anyway, here's an example. In the previous video, we saw a basis for R3 being I, J, and K, essentially, right? 1, 0, 0, 0, 1, 0, 0, 0, 1. Well, here's another set of vectors, and I want to see if maybe it might be a basis instead, right? The thing is, it turns out that the basis of a vector space is not unique. You might have many, many different ways of picking vectors to be a basis. Uh, here's my example here. Let 1, 2, 3, 1, 0, 1, and minus 2, 3, 0. Those three vectors. I want to see, are they a basis? Well, how do you get to be a basis? Well, first of all, you have to span the space, right? The span of these three vectors has to be all of R3, and they have to be linearly independent. So let's check those things. To show that they span, we need to show that if you pick any vector in R3, I'm going to call it A, B, C, then I can find a way to write this vector as a linear combination of those three. So that is, I need to take some constant times the first one plus another constant times the second one plus a third constant times the third one, and it has to all add up to A, B, C. Well, this single equation in R3 vectors is actually I can rewrite it as three equations of real numbers. That is, the first components, whatever the first component on the left-hand side turns out to be, has to equal A. Second components has to equal B. Third component has to equal C. So the first component is 1 times K1 plus 1 times K2 minus 2 times K3. That should be a subscript K3. That's better. Likewise, second coordinate should be 2K1 plus 0K2 plus 3K3 has to equal B. And the third coordinate says 3K1 plus 1K2 plus 0K3 has to be C. So there's a system of three equations and three variables. And we know something about how to solve it. If you're given A, B, and C, you can do the stuff we did back in chapter 1, right? I want to just write this as a matrix equation for now and see this matrix is the coefficients from here. The variables are K1, K2, and K3. And this vector over here is, well, whichever vector it is we're trying to add up to, right? Now, there's some things we know about this system. Again, back from chapters 1 and 2. That is, we know that this system has a solution for every single vector you put over here if, and only if, this matrix is invertible, right? There's this whole theorem we had of the following are equivalent. Well, one of the things equivalent to being invertible was that this matrix equation has a solution for every vector you put here if that's invertible. And if you have a solution for every vector you put here, then yes, that has to be invertible. Also, we know that if it's invertible, then the determinant is not equal to 0. So to show that this always has a solution, no matter what A, B, and C are, then I would just have to show that the determinant of this is not equal to 0. Now, take a look at the test for linear independence. To show that these three vectors are linearly independent, what I need to do is I need to look at a linear combination of them adding up to 0 and see if I can get that to happen with K1, K2, and K3 maybe not equal to 0. Certainly it works if they are 0, but are there any others? If there are no others, then they are linearly independent. Well, this one equation of vectors in R3 can be converted into three real equations. because if this vector on the left equals that vector on the right, then they have to be equal in every component. So the first component, k1 plus k2 minus 2k3 has to equal 0, right here. Second component is 2k1 plus 0k2 plus 3k3 has to equal 0. And likewise, third component is 3k1 plus 1k2 plus 0k3 has to equal 0. Well, that's this system right here of three equations and three variables, k1, k2, and k3. Written as a matrix form, it looks like this. Notice that the coefficient matrix down here is exactly the same as the coefficient matrix we had up there. So, and also remember that theorem that said the following are equivalent. Well, one of the things that was equivalent was that the matrix, the coefficient matrix here is invertible if and only if the homogeneous system has a unique solution. Well, that's precisely what we're looking for. We're looking for this to have a unique solution. If it does have a unique solution, namely 0, 0, 0, then those vectors are linearly independent. So this will have a unique solution if the matrix is invertible, which also is equivalent to, well, equivalent to this having a solution for any A, B, and C, and it's equivalent to the determinant is not equal to 0. And so the question is, what is the determinant of that matrix? Well, it happens to be 2. So that matrix right there is invertible, which means this has a unique solution, which means those three vectors, which happen to be the columns of the matrix right now, 1, 2, 3, 1, 0, 1, and negative 2, 3, 0. Those were the vectors I started with back up above. Well, yeah, there they are. 1, 2, 3. They are linearly independent. And up here, it shows that no matter what A, B, and C you choose, if this is invertible, then you can find K1 and K2 and K3 by just multiplying both sides by the inverse. Okay. So, yes, it is a basis. Curious thing to me about this, one curious thing about this example is that in general, if you randomly grab three vectors out of R3, they will be a basis. They will form a basis. They'll be linearly independent and they'll span. It's only by chance that you might happen to get ones that either don't span or aren't linearly independent. That is more likely than not you will get ones that do form a basis. And so when I randomly wrote down three vectors, I wrote down my favorite vector, 1, 2, 3, and then I grabbed another one and then just randomly another one. What I had initially was minus 2, 3, 1. And it turned out that the determinant with a 1 right down in this spot right here was 0, and they were not a basis because they neither spanned nor were they independent. So anyway, I had to change that to something else so that they would be. And the determinant is 2, so they form a basis. Matrices. Here's in M22 we have the standard, what's called the standard basis. 2 by 2 matrices. I'm going to put zeros everywhere except for 1 in the upper left. This one I have a 1 in the upper right, lower left, lower right. And that, it turns out, is a basis. To prove it's a basis, well, you could check. Can you take any 2 by 2 matrix and write it as a linear combination of these 4? And actually, I have the linear combination right here. If you're trying to do A, B, C, D, well, multiply this one by A. That would put an A right here. And 0 times A is still zeros over there. Multiply this one by B, which puts a B right there and leaves those as 0. And multiply by C. The C goes right here. C times 0 is always 0. And D gets you right there. Add them all up, and you'll get this. So yes, it does span. No matter what 2 by 2 matrix you get, you can write it as a linear combination of those 4. Likewise, are they linearly independent? That is, can you get a linear combination like this to add up to the 0 matrix? And, well, a linear combination like this is going to look like that. And is there any way to make this equal to that? Well, yes, there is. Make A equal to 0, make B equal to 0, make C equal to 0, and make D equal to 0. And that's the only way to do it, because for this matrix to equal that matrix, they have to equal in every component. And so you have a basis. Now, there are other bases for M22. Again, if you just randomly grab 4 matrices, 2 by 2 matrices, they probably will form a basis. Again, it's more likely that they are a basis than they aren't. If you choose 5, it's going to turn out it won't work because they will be linearly dependent. Or if you only choose 3, it's going to turn out that they don't span. So for some reason in M22 you need 4 things to make a basis. And that's going to be the topic of the next section on dimension. But in the meantime, we have one more thing that I want to talk about here, and that is the following theorem. If S is a set of vectors, finite set of vectors, is a basis, if this is a basis for a vector space V, then every vector V in the vector space can be written as a linear combination of those. That's no surprise, because if it's a basis, they span. But more so, in a unique way, that you can write V as a linear combination of these vectors, but only one way. There's not 2 different ways to do it. Okay. So here's my proof. Suppose that you can. Suppose that you've got a vector V that can be written in 2 different ways. Right? Before I go on with that, let me just say, because I know S is a basis, I know that it does span the space so that every vector can be written as a linear combination in at least one way. And I'm trying to show that it is only one way. Right? So the thing is, if it could be done in 2 different ways, if this combination and that combination are equal to each other and equal V, then what I'm going to do is I'm going to take, I'm just going to ignore this equation right here and focus on this one, and subtract all this stuff on the right over to the left. So here's all the stuff that was on the left minus all the stuff that's on the right. When I subtract it all off from the right-hand side, I'm left with a 0 vector over there on the right. Now I'm just going to use the properties of the operations in a vector space. I didn't say what vector space I'm in, but I know that in a vector space I have a distributed property. So this minus sign, essentially -1, can be distributed in to each one of these things here. I know I have a commutativity property, so I can add in any order I want. So I'm going to start with this one, and then I'm going to grab that one, and then this one, and then that one, and so on down the line. So I get the V1s together, I get the V2s together, I get the V3s together, and lastly the Vn's together. Right? And then I've got another distributed property that allows me to pull the V's out. So from these 2 terms right here, factor out a V1. So that's K1 minus C1 times V1. Likewise, factor out the V2 from those 2, and the V3 from the next 2, and the Vn from the last 2. Okay. So what I end up with is some number times V1 plus some other number times V2 plus and so on times an nth number times Vn equals the 0 vector. But now I know that the V's are a basis. And if they're a basis, they have 2 properties. They span and they're linearly independent. In particular here, they're linearly independent. So if they're linearly independent, any linear combination that adds up to the 0 vector must be the trivial combination, right? It must be 0 times V1 plus 0 times V2 all the way up to 0 times Vn. That's the only way to do it, adding up to 0. Okay, so look at what happens now. If this K1 minus C1 is equal to 0 and K2 minus C2 is equal to 0 and so on, then you must have K1 equals C2, K1 should equal C1. There's a typo there. K1 equals C1, K2 equals C2, and Kn equals Cn, which means that what you thought were 2 different ways of taking linear combinations of the V's are actually the same one. That the coefficients over here are the same as the coefficients over there. What's happening here is essentially the uniqueness, because of the linear independence, you're saying that this equation is unique. If you've got a linear combination adding up to 0, there's only one way to do it. But that generalizes then to saying if you've got a linear combination adding up to any particular vector, V, then that's the only way to do it. Right? If you have linear independence, then linear combinations are unique. If you have spanning, then every vector can be written as a linear combination. If you have both, then every vector can be written as a a unique linear combination. There's only one way to do it. Okay? And that's the really beauty of, one of the real beauties of having a basis, that every single vector can be written as a linear combination in a unique way. What's going to happen later on is that once you can look then at, when we start doing transformations and things, you can look at what happens to the basis and be able to tell what happens to the whole space. Right? That you can look at just a finite number of things and understand what's happening for all the infinite vectors that are in the vector space. Okay? The thing that I want to end with is that although a vector space may have many, many bases, each time you pick a basis, then every vector is uniquely described in terms of that basis. And we'll use that in the next video to talk about coordinates.